So in these problems, we want to evaluate the limit as x approaches infinity of these three functions. Okay, let's start with the first one. The limit as x approaches infinity of 1 minus x over 2x. So as someone pointed out, yes, the shortcut rule is to say, well, the leading coefficient of the numerator is actually -1. The typical order is to put the highest powers of x first, so you would actually write -x plus 1. But because x is the highest, has the highest power of the two terms in the numerator, its coefficient is the leading coefficient, -1 right here, divided by 2. So the limit is going to equal -1/2. The way you show that, and you do need to be able to show it, is you multiply by 1 over the highest power of x over itself. So the highest power of x I see in this problem is x to the first. So I'm going to multiply by 1 over x over 1 over x. I'll add some parentheses right there because I'm going to distribute that out over the numerator. So 1 times 1 over x is 1 over x. Then -x times 1 over x is -1. In the denominator, 2x times 1 over x simplifies 2. Now as x goes to infinity and gets really, really large, the value of 1 over x is going to approach 0. So we're left with 0 minus 1 in the numerator divided by 2. So we get -1/2 for the first limit. The second limit is the limit as x approaches -infinity of 1 minus x over x squared. So because the highest power of x is this 2 right here, 1 over x squared, on this one we're going to multiply by 1 over x squared over itself, over 1 over x squared, and distribute, add parentheses if it makes it easier for you to see. So first is 1 over x squared times 1 is 1 over x squared. Carry my limit along. So 1 over x squared minus x times 1 over x squared. One of those x's cancels, so we're still left with 1x in the denominator. All over in the denominator, x squared times 1 over x squared is 1. So in the numerator, both of those terms are going to approach 0 as x gets really, really large. Even though it's approaching -infinity, these denominators get so big that compared to the numerator of a constant 1, eventually they'll get close to 0. Actually, pretty quickly they do. And the denominator is 1, so we have 0 over 1, which is 0. And you get the idea. And the last one, the limit as x approaches positive infinity of 1 minus x squared over 2x. The highest power of x is a 2 right here, that x squared. So I'm going to multiply by 1 over x squared over 1 over x squared. Always make that middle bar a little bit bigger so it's clear which is the big fraction. So the limit as x approaches positive infinity of distributing. Okay, 1 times 1 over x squared is 1 over x squared. Minus x squared times 1 over x squared is -1. Then 2x times 1 over x squared is going to simplify to 2 divided by x. Okay, so as x goes to infinity, that term and this term both go to 0. So this approaches 1 over 0, which is undefined. Okay, so for this one, the limit, well, when we do it this way, we get undefined. But what that really means, though, is that you basically have a constant divided by a really, really small number. So this one I was hoping somebody would ask about because it is a little bit more complicated, and this example is really just to push you guys because we didn't see one exactly like this in class. But what I wanted you to do was to look at the graph of 1 minus x squared over 2x. So I'm going to open the graph of that up real quick. Okay, so here is the graph of y equals 1 minus x squared over 2x. So the limit that we are finding is the limit as x approaches infinity of this graph. We want to say what do those y values approach as x gets infinitely large. Okay, so here's the graph. Hang on. There we go. Okay, so it goes down, down, well, and it keeps going down. So I'm going to zoom out a little bit here. Whoa, there we go. And as I zoom out, you see this x is getting bigger and bigger. you can tell that these y values just keep going down forever, okay, which is kind of what would happen if you plugged in, if we did it numerically, and we plugged in real large values of x, we would just keep getting, well, smaller and smaller values of y. It just keeps going down. So that limit actually equals negative infinity. In class, I think when we did problems like this, for the most part, we were finding horizontal asymptotes, so I would have said this one has no horizontal asymptote. The horizontal asymptote on this one would be y equals 0, and on the first one would be y equals negative a half. But if you get that there's no horizontal asymptote, it does not necessarily mean that the limit doesn't exist. It just means that you maybe need to take a second look at it or work it another way. So if you have any more questions on those problems, please let me know.